Starting our third unit here. Our third unit is going to focus on all of those functional groups that contain that carbon-oxygen double bond, our carbonyl bonds. And we're going to start out with aldehydes and ketones. Okay. So just to remind ourselves here, an aldehyde is where we have that carbonyl group located at the very end of a molecule. That means that there's necessarily a hydrogen, at least one hydrogen, bonded to that carbonyl carbon in an aldehyde. Whereas a ketone is if we take that molecule and we move that carbonyl group into one of those internal positions. So that carbonyl carbon is bonded to a carbon on either side. That would be a ketone. Excuse me. Alright, and again, this understanding these functional groups, as well as a lot of the ones that we're going to be talking about going forward here, right? There are other functional groups, carboxylic acids, esters, amides, that also contain these carbonyl compounds, or these carbonyl bonds. So just focusing on these carbonyl bonds for a second. Alright, if we kind of zoom in, okay, this carbon-oxygen bond here. What do we know about these carbon-oxygen bonds? Are these polar, non-polar? Polar. And where is that electron density going to be? On the oxygen or the carbon? On the oxygen. That more electronegative oxygen is holding that electron density, pulling that electron density away from that carbon, leaving it relatively electron deficient. All right, so these bonds here are polar bonds between our carbon and oxygen. All right, so carbonyl bonds are polar bonds. Okay, so that means this molecule has stronger forces than just those really weak dispersion forces that only nonpolar molecules have. But there are two types of polar interactions, dipole-dipole and hydrogen bonding interactions. Can two of these acetone molecules hydrogen bond with one another? All right, what bonds do we need in order to be able to hydrogen bond? Give me an example of something that can hydrogen bond. Oxygen, yeah, not all by itself though. You need a hydrogen. All right, so an alcohol group would be an example of something that could hydrogen bond. You have to have either an oxygen hydrogen, nitrogen hydrogen, or fluorine hydrogen. These are the only bonds that can hydrogen bond. Okay? So if we had like water with acetone, the oxygen could play the role of a hydrogen bond acceptor, but two acetone molecules cannot hydrogen bond with one another. These things can only dipole-dipole interact. And dipole-dipole interactions are what? Stronger or weaker than hydrogen bond interactions? Weaker. All right, so in terms of our physical properties, okay, we would say that these bonds these compounds are polar. So physical properties. aldehydes and ketones would be a polar functional group. Again, because they can dipole-dipole interact. Okay, and we can talk about the strength of these interactions. We can compare them using boiling points. So let's take a look at boiling points. And we want to compare similar sized molecules because, of course, bigger molecules have higher boiling points than smaller molecules, relatively speaking. All right, but what we want to compare is molecules of a similar size. And we're going to compare nonpolar versus our polar functional groups. Okay, let's take a very nonpolar molecule. Something like methylpropane here. Because this is a nonpolar molecule, it has only those weak dispersion forces between it and its neighbors. All right. So this molecule here has a boiling point of negative 12 degrees Celsius. Right? It's actually a gas at room temperature. It has such a low boiling point. If we take an example of a very polar functional group, what makes this hydroxyl group here so polar? It can do what type of interactions? Hydrogen bonding. All right, it's got a boiling point more like 83 degrees Celsius, so quite a bit higher. Okay, and again, that boiling point being a measure of how strongly these molecules are interacting with their neighbors. You got to put in this much thermal energy in order to break those interactions and get these molecules into the gas phase. But now we're looking at our carbonyl compounds. All right, so again, doing similar size here. We're going to look at acetone. Acetone would be considered a polar functional group, but its interactions are not quite as strong as that of its hydrogen bonding alcohols. This has a boiling point of around 56 degrees Celsius. And again, not as strong of interactions because this thing can only dipole-dipole interact with its neighbors. Okay, so yes, definitely on the more polar end of the spectrum here, just not quite as strong as our polar functional groups that can hydrogen bond. Still way stronger than our dispersion forces. All right. We're going to start where we normally start with our functional groups. And that is talking about nomenclature. And we're going to start with aldehydes for our nomenclature discussion. In order to kind of better understand through analogy how we're going to name these things, we're going to get an alcohol down here as well so we can compare. Everybody's going to take a second and name this alcohol for me. We got these 4 carbons here and our alcohol functional group. Alcohol functional group is located on carbon 1. So this would be 1 bute. And then we have this AN in our name here, butanol. And what is the AN telling us? All carbon-carbon single bonds, right? So we got our total number of carbons, the bute. We have the AN to indicate all carbon-carbon single bonds. And then we have that OL ending for our functional group. And then, of course, the locant of that functional group on carbon 1. All right, so then we're going to take this alcohol and we're going to oxidize it. Right? Remember, we can take alcohols, primary alcohols specifically, and oxidize them to make aldehydes. So replace that carbon-oxygen single bond with a carbon-oxygen double bond. Cool, so how are we going to name this thing here? So step 1, when we do our parent chain, since we have a new functional group, our aldehydes, we're going to have a new suffix that we use at the end. Whereas alcohols were OLs, all aldehydes are ALs, al. All right, we're not going to see anything new with our substituents. And when we number our parent chain, we're going to prioritize that functional group just like we always do. All right, so I have my 1, 2, 3, 4 carbon parent chain. So again, we have that prefix bute. We got all carbon-carbon single bonds here, so that's same AN. All right, so number of carbons, all carbon-carbon single bonds, and now we're going to change our ending from the OL to an AL, butanol, right, for our aldehyde functional group. Now when we number our parent chain, we're going to make sure to prioritize that functional group, all right? But what if I were to move that carbonyl group over 1 carbon? Put it over here. Would that still be an aldehyde? No. So I wouldn't have that as my aldehyde, wouldn't have that AL ending. And what if I moved it all the way over to this side? What's that going to do to my numbering? I'm just going to number in the other direction, right? So is there any other possibility then for that carbonyl group to be on carbon 1? No. By definition of an aldehyde, it's got to be located on the end. Whatever end it's located on, we're just going to make that carbon 1. So when we do our nomenclature for our aldehydes, we do not include the locant. So it's not 1 butanol. The 1's implied by the fact that it's an aldehyde. It is just butanol. What's up?
What if you had another functional group on there? Does that one have priority?
We'll talk about that.
Okay.
Yeah, we'll graduate to that. All right, and then 4, if we did have multiple substituents, we would assemble them in alphabetical order. Nothing different there. All right, so all we got to update is the fact that we have a new functional group, so we have a new suffix. The weird thing about this functional group is by definition it has to be located on the end of a molecule or on carbon 1, so we don't bother including the locant when we name it. So although this is 1 butanol, this is just butanol. Okay, so now let's graduate to our nomenclature of ketones. All right, again, let's do an alcohol so we can compare. Everybody's going to name this alcohol for me. All right, we'll get there. Oops. Where did I go? There we go. All right, so this would be 2, I guess just to be clear. We got our parent chain, our 5 carbons. This alcohol group is located on carbon 2, so this would be 2 pentanol. All right, now that we're talking about ketones, we got a new functional group, and these have a different suffix than aldehydes. Ketones use that O-N-E ending, own. All right, so let's take this alcohol here and let's oxidize it to create our ketone. All right, using this terminology from our previous chapter, remember primary alcohols can be oxidized to aldehydes, whereas secondary alcohols can be oxidized to ketones. Okay, again, nothing new about our substituents. Okay, but when we number this parent chain here, we got our same 5 carbon parent chain. We're going to number it in such a way that we prioritize that functional group. So we're going to put it on the lowest possible number, which would be carbon 2. For ketones, do I have to include my locant in the name? If I picked this carbonyl group up and moved it over here, is this still a ketone? Yes, and it's a different ketone, right? So it's going to be a different molecule depending on whether it's located on carbon 2 or carbon 3. So yes, we have to build it in the name. So this would be 2-pentanone. Right? Whereas this was 2-pentanol, this is now 2-pentanone. Importantly, the big distinction between ketones and aldehydes is we do include that locant in the name for our ketones. All right, and that 4th step, when we assemble everything together, those are all the, nothing new there. Okay, so the big distinction is we have our new ending here, our new suffix for ketones and aldehydes. For aldehydes, we use the suffix -al. For ketones, we use the suffix -one. And the big difference between these two functional groups is aldehydes always being located on a terminal carbon means that they're always on carbon 1, so I don't have to include the locant. Whereas my ketone could be anywhere in the middle of my molecule here, so I do include the locant. All right, we'll practice this in a second, but the last thing to discuss is we got to update our functional group priority list, right? We had this master list here. I guess let's just reset it. We had this master list here of our functional groups that we covered, and we said that for each of them, they have a suffix as well as, a suffix as well as a prefix. So we talked about how when we had molecules with 2 functional groups, we referred to the lower priority functional group by its prefix and the higher priority functional group by its suffix. All right, so now we have to update this list here. It turns out that our aldehydes and ketones are higher priority than all of these other functional groups here. Specifically, aldehydes are our highest priority, at least at this point in the course, followed by ketones. All right, what suffix do we use for aldehydes? Al. And we do a real hard A, so we make sure to distinguish them from alls, right? Because you can kind of tend to sound similar. All right, and then ketones, we use the suffix -one. But in terms of their prefix, all right, aldehydes and ketones actually share the same prefix. They are referred to as oxo groups, should they be the lower priority group in a molecule. Cool. All right, so let's practice this. I'm going to give you all a few minutes to name the following compounds. let's go through these. I'm going to find my parent chain, my longest continuous set of carbons. And I guess actually just to take a step back, do I have an aldehyde or a ketone? Aldehyde. So I have my 6-carbon parent chain. I have my aldehyde functional group here. So I'm going to use that Al ending. I'm going to number my parent chain. And remember that aldehyde functional group always gets carbon 1. Let me make some room here. So that means over here on carbon 4 is a methyl group. So putting this all together here, we have 4-methyl. And then I'm not going to include that locant, right? So hexanal. Okay, over here I have these 5 carbons. This is a ketone or aldehyde. Ketone. And these are just halogen groups here, substituents, a chloro substituent, a bromo substituent. I can number this parent chain 2 different directions here. All right, which one of these numbering schemes is going to be correct, red or blue? Red, because I'm going to prioritize that functional group, but since there's a tie, when I prioritize that functional group, I'll break that tie by looking at my other substituents. So indeed, I want that red numbering scheme here. So putting it all together and making sure to assemble in alphabetical order, this would be 2-bromo, 2-chloro. Am I going to include the locant for my ketone group or not? Yes. Yeah, got to include that in there as well. So 3-pentanone. All right, and with aldehydes, you wouldn't be able to do this because, again, we don't indicate the locant of our functional group. But for ketones, we could also do that other perfectly acceptable IUPAC way of naming, where we put our locant of our functional group right in front of that functional group suffix. So 2-chloropentan-3-one would also be perfectly acceptable. Either one of these would work. All right, here, now we have some mixed functional group molecules. All right, and importantly, we got to go to our priority list. This one right here is what? Alcohol, and this one right here is what? Ketones. So that means I'm going to compare my alcohol and ketone. Ketones are the higher priority functional group, so I'm going to refer to that by its suffix, and I'm going to refer to the alcohol by its hydroxy prefix. So this thing is no longer special. It is demoted to a substituent, specifically that hydroxy substituent. All right, here's my ketone functional group. So then I'm going to find my parent chain. I got my substituent. I'm going to number my parent chain. And which numbering scheme am I going to pick, red or blue? Because I'm going to prioritize that highest priority functional group there, right? So I'm going to use this red numbering scheme here. So this would be 5-hydroxy, 3-hexanone. All right, now in this molecule here, I have these 2 carbonyl groups, but importantly, they're different functional groups because I got one in the middle here, a ketone, and I got one in the end, an aldehyde. So my higher priority aldehyde, I'm going to refer to by that Al suffix. My lower priority ketone, I'm going to use that oxo prefix. All right, so my 4-carbon parent chain here, my substituent is that ketone functional group, which has now been demoted to an oxo substituent. When I number my parent chain here, I'm going to prioritize that functional group, make sure that that aldehyde group is on carbon 1. So this would be 2-oxo-butanal. I again don't have to indicate where my aldehyde functional group is because it's always going to be on carbon 1. All right, and then 2 more to do. We'll do real quick together. This molecule also has these 2 carbonyl groups. All right, same with this one. Okay, but before one of them was an aldehyde, one of them was a ketone. In this case, these are both ketone functional groups. So how am I going to put this into my name? What did we do when we had 2 alcohols in the same molecule? We used that di, right? Those were diols. So this would be a dione here. So going through and finding my parent chain, I got these 7 carbons. I'm going to number my parent chain. So this would be 2,4-hept and dione. And what's wrong with this name here? Heptanedione. 2 consonants. So what are we going to keep in the middle here? Yeah, not hepten, but we're going to make it heptanediol. All right, so then using that same principle, take a second and name this functional, or this molecule rather, over here. Right, and instead of a dione, this would be a dial. All right. Is there any other way to make this dial? So propane dial. Right, 3 carbons long. We're going to retain that E. So propane dial. I got 1 aldehyde group on carbon 1 and 1 aldehyde group on carbon 3. Would there be any other way to do this molecule? No. So if you have a dial, you know one's located on one end, one's located on the other end. So just like before, we do not have to include our locants. This would just be propane dial. Cool. All right. So now we're going to transition into our reactions. Oh, I lied. One more special case, one more thing, all right? Just to note, we have our special aldehydes and ketones, 1 of each, like a special aldehyde and ketone. This just goes in our nomenclature section here. There are one aldehyde and one ketone, that were just so famous before the IUPAC system came about that they have their own common name that doesn't follow the same logic of our systematic IUPAC names. One of them would be this one here. If you did our IUPAC systematic naming, this one would be propanone. But nobody calls it propanone. What do we call it? This is the most famous, you no doubtedly have used this a billion times, even just to wash your glassware in organic chemistry. This is acetone, all right? So nobody calls acetone propanone. It's got its own common name that just sticks, so much so that the IUPAC's given up and they're like, yep, we're just gonna call this guy acetone. So this has its own special name here that we just gotta know. This is acetone. All right. Likewise, our smallest aldehyde, less famous in chemistry, more famous in biology, specifically if you're dissecting animals here. This is not methanal, which would be its IUPAC systematic name. Right? Nobody calls this methanal. This is what's called formaldehyde. All right, so these are two, kind of like how methyl benzene was really toluene, and we just had to know that and be able to recognize it. Same sort of idea here. These ones do not follow our systematic naming laid out by the IUPAC. Their common names have just been adopted as the name of those molecules. So these we just got to be able to recognize. Okay, my bad. So now we'll transition into reactions of aldehydes and ketones. All right, and the key here to understanding our reactions of aldehydes and ketones is exactly what we were saying about this polar carbonyl bond here. We've seen aldehydes and ketones as reactants before, and they're always playing the same role in a chemical equation, chemical reaction rather, which is what? The role of an electrophile or a nucleophile? No, so look, it kind of be tempting to say either because we do have these lone pairs up here. However, turns out that this oxygen is a terrible nucleophile. Every once in a while, you will see it play the role of a proton acceptor, of a base, where it does reach out and grab a hydrogen. But 99.9% of the time that we're talking about carbonyl compounds and their chemistry, the key to understanding that is this electrophilic carbonyl carbon. And this is something that you just need to have ingrained in your brain. Chant it to yourself over and over again. Electrophilic carbonyl carbon. All right? We laid out a list of electrophiles. Carbonyl carbons were on it. All right? We laid out a list of nucleophiles. Carbonyls were not on it, right? So carbonyls are always playing the role of electrophiles. And the first reason being our carbonyl carbon is relatively electron poor. Right? It lacks electron density. Because of that polar bond where that oxygen is pulling all that electron density onto itself. Okay, but remember the other feature of an electrophile, there are plenty of polar bonds that still aren't electrophiles. Electrophiles also have to be able to accept electron pairs. And these carbonyl carbons are particularly good at accepting electron pairs. So why is that? So let's take a nucleophile here. It's got its negative charge, so I know it's a nucleophile. And it's going to do what nucleophiles do and attack this carbonyl carbon. Well, if I stopped there, that'd be illegal. I would have broken the octet rule of that carbonyl carbon. But what always happens when our carbonyl carbon gets attacked? Do we stop there? No, what else can we do? This pair of electrons jumps up onto our oxygen, playing the role of a leaving group, right? Our electrophiles, they have to have polar bonds, but they also have to have a leaving group, so they can actually accept electrons. So this can accept pairs of electrons because it's got that built-in pi bond leaving group. That more electronegative oxygen is more than happy to accept that pair of electrons. And so this carbonyl carbon can get attacked without ever breaking its octet, right? So again, electrophiles, they need to lack electron density. They also need to be able to accept electron pairs, and our carbonyl carbons can do both, which is why they are good electrophiles. All right, there's also one other feature that makes these carbonyl carbons good electrophiles. Remember we talked about last chapter a lot about accessibility, how a nucleophile needs to be able to get to that electrophile in order for a reaction to occur. So those carbonyl carbons are also nice and accessible. All right, why is that? Well, because this sp2 hybridized carbon has a trigonal planar geometry. It's not a crowded tetrahedral geometry. It's this nice flat region of a molecule where an electrophile can, or rather a nucleophile can very easily get to, right? So it's nice and accessible because it's got that trigonal planar geometry. All right, so 99.9% of the reactions that we're going to discuss in this chapter are going to correspond to this key right here, the fact that that carbonyl carbon is going to play the role of an electrophile. Again, you want to have down pat in your mind, electrophilic carbonyl carbon. That needs to be something that we just kind of chant to ourselves whenever we're talking about reactions of aldehydes and ketones. And we're going to see a ton of these reactions, but I'm actually going to end here with one sort of key difference between aldehydes and ketones. All right, so we're going to say aldehydes and ketones, they share most reactions. But there's one key reaction that they do not share, which is what we talked about last chapter. Those oxidation reduction reactions. And this is, historically speaking, why these are considered two different functional groups. I have a feeling if we redid everything nowadays, we would call these all ketones, and we would call them terminal ketones instead of aldehydes, and internal ketones instead of ketones. But historically speaking, these were divided up into two different camps because they do not share this one key reaction, which was kind of easy to do back in the day, all right? And that is these oxidation reduction reactions. So let's just remind ourselves, we can take an aldehyde, and if we treat it with an oxidation agent, like our sodium dichromate in dilute sulfuric acid, what do we get? What does an aldehyde oxidize to? A carboxylic acid. And if instead we took that same 3 carbons, but instead we were talking about a ketone, again, a famous ketone that's got a special name, acetone. What does acetone oxidize to? That'd be reduction. Can we oxidize it? No. All right. So very simply, the difference between these two functional groups, and really why they're classified as two different functional groups, is because of this reaction right here. Aldehydes can be oxidized, but ketones cannot. All right, historically speaking, this was a big deal because one of the first things that we started studying in chemistry/biochemistry was sugars, and it turns out that sugars can be divided up into sugars that have aldehyde functional groups and sugars that have ketone functional groups. And they would look at these two sugars and be like, dang, they have the exact same chemical formula, but some can be oxidized and some can't. Let's separate these into these two camps, and that's why we have these two different functional groups, all right? They do not share this one reaction here, which is really key. What they do share, and what we're going to cover to death in this chapter, is the fact that that carbonyl carbon is electrophilic, and we can do these nucleophilic addition reactions. And so that's where we're going to pick up next time.